The purpose of this experiment is to discover how a motor neuron can regulate the force produced by a muscle. I'm going to show you how to set up and stimulate the hind leg of a locust. Notice in the muscle the herringbone-like pattern on the cuticle of the femur. Each block on the herringbone is where a block of the extensor tibia muscle attaches to the cuticle. The other end of the muscle block fastens to the tendon, which is like a flat strap that stretches along the length of the femur. So the muscle has a pennate structure, a bit like a feather. The central quill of the feather is the tendon, and the muscle blocks pull on it at an angle. This enables lots of muscle fibres to pull in parallel with each other, enhancing the muscle strength. For this experiment, we're going to need a perspex holder with pin electrodes, a pulse generator, spring balance, a £1 coin, elastic bands, and a locust leg. To begin with, we're going to take out the locust leg and making sure that it's at a right angle to the perspex, I'm going to gently place it on. Then we need to roll up the elastic bands to make sure that the leg doesn't fly off after the first kick. Then plug in the power generator, set the dials to 0, press the enable button. Keep turning the amplitude up until you see the leg twitch. Once you see it, put it carefully over your finger and see if you can feel it. Let everyone do that in the group. Then turn it slightly above that so that you know you'll get a consistent kick. One question you'll be asked to test is whether increasing the amplitude increases the force of the kick. So this just slowly increase the amplitude, but be careful not to hold down the enable button for more than 1 second, as this could damage the muscle. For the next part of the experiment, we're going to measure more accurately the force produced by the leg. And to do this, we're going to use a spring balance. To do this, we take the thread and we loop it through the perspex holder and attach the hook onto the leg at the end of the tibia, not on the foot because the foot is floppy and could break. We put the amplitude up high enough so that there's enough power to cause the foot to kick, but we keep the frequency down low. For the first reading, check what the force on the spring load is. In this case, it's 1.9. And measure how far it goes. It goes all the way down to 3.5. So you measure the difference between the 1.9 and the 3.5, and that is the force produced by the leg. Here are a set of results we produced. If you can, produce 2 sets of data. Using these values, you can make a graph to produce in your lab sheet. Now we're going to see if the locust leg can lift the pound coin. Simply place the pound coin into the paper clip and hook it onto the end of the tibia. Like so. You should be familiar by now with how much power the locust leg needs. Turn it up. You can see that it does actually lift the pound coin.
Now we're going to look at the mechanics of how a locust jumps and use physics to help us calculate the force produced. In order to understand how a locust jumps, we are going to use the simple wooden model. The screw is where the tibia pivots at the end of the femur, and the tendon of the extensor muscle inserts quite close to the pivot. This means when the knee is at a right angle, the force with which the muscle pulls on the tendon is much greater than the force with which the foot is being pushed. The extensor muscle tendon attaches to the cuticle 0.63 mm away from the knee pivot. The tibia is 22 mm long. So, to convert the force you measured at the foot to the force with which the muscle pulled on its tendon, you need to multiply your measurement by 22 and divide by 0.63. Here is a locust preparing to jump. Notice how, before jump, it crouches down and remains with its legs fully flexed. In that time, it is building up force in its extensor muscle. We can work backwards from a locust jump to find out how much force it applied to the ground during a jump. This needs physics, and you do not have to remember the details. The full instructions are given in the lab. You will measure how high and far a real locust jumps, and then work out how much force is needed for its jump. The point of doing that is so you can compare this with the maximum force you have measured that the extensor muscle can exert.